Welcome. In the last class I told you that in addition to galaxies, our universe is also filled with another kind of component, which is the cosmic microwave background radiation. And at the end of the last class we were trying to figure out what happens to the cosmic microwave background radiation due to the expansion of the universe. So let us resume that discussion. So we were looking at a comoving volume, a volume of unit comoving length. So the volume is a cube, and we are assuming that the expansion of the universe is adiabatic. Entropy is not generated in this process. So we then applied the first law of thermodynamics to the cosmic microwave background in this volume. So the entropy of the cosmic microwave background inside this volume should remain unchanged due to the expansion. So it should satisfy this. PdV plus the change in the internal energy should be 0. Now we will do a somewhat general derivation now. So we will assume that the pressure, so the medium material which is there inside, we will assume that the component that we are discussing, the substance that we are talking about, the pressure can be written as W times the internal energy density. This is the equation of state. And for the CMBR, cosmic microwave background radiation, we have discussed this already. For a photon blackbody spectrum, for photon isotropic distribution of photons, the pressure is 1/3 the energy density. We have discussed this when we were discussing, we have learnt about this when we were discussing the radiative transfer and blackbody spectrum, right. So W has a value which is equal to 0. W has a value which is equal to 1/3. We have also right in the beginning of our discussion of cosmology, we have also talked about galaxies, and galaxies do not exert any pressure. They do not, their random motions are very small. That's an observational fact. Okay, so they sit where they are more or less, whereas photons move at the speed of light and they carry momentum with them. So there, if you have a gas of photon, there is always a momentum flux through any surface. A gas kind of galaxies distributed in space, they will sit where they are and just expand with the universe. Okay, so galaxies and stuff like this, like that, are referred to as dust. This is general relativistic parlance. Okay, so in general relativity, such things which do not have pressure are referred to as dust, and galaxies are an example, and W is 0. So our discussion is going to be for a very general class of is going to encompass both of these. And for galaxies, we have already seen from the conservation of mass that the density into a cube should be a constant as the universe expands. Okay, but for something else, for other things which have pressure, it is not the conservation of mass which is important, but the first law of thermodynamics, which is essentially the conservation of energy. Okay, so if there is expansion, the material can do work, and that the energy will come from the internal energy. That has to be accounted for. That is the basic consideration. Okay, so let us now do this calculation. So the pressure can be written as W into the energy density, and this is going to be dA cube plus I have the energy density here into a cube, the volume is a cube. So I can write this as U dA cube plus a cube du is equal to 0. and I can now combine these two terms and divide throughout by a cube. So, if I combine these two terms and divide throughout by a cube, what I will get is 1 plus w dA cube by a cube plus, and I divide throughout by u also, the internal energy density. So, du by u is equal to 0. Okay. So, now we can do this integration, it is quite straightforward. This integral is log a cube to the power 1 plus w. This integral is log u. So, what this tells us is that the a cube into 1 plus w into u energy density is a constant, which I can write as u naught, because we have assumed that the scale factor has value 1 at present. So, we are led to the relation that in general, if there is pressure, it is okay. If there is, first of all, it is more convenient to work in terms of the mass density in terms of energy density instead of energy density, the two being related like this. Okay. So, the mass density is the energy density divided by c square rho. Okay. So, then we are led to the relation that the rho a to the power 3 1 plus w is equal to rho naught. Okay. So, for dust we see that rho a cube is constant, rho naught. So, for dust rho, the dust is the ordinary matter. So, rho matter a cube is equal to the and for any kind of relativistic isotropically distributed relativistic particles, the pressure is 1/3 the energy density. So, for any kind of for or even or just for the CMBR, let us say, does not matter, this is 1/3. If it is 1/3, then we have rho a to the power 4 is a constant. So, for the cosmic microwave background radiation, it is rho gamma a to the power 4 is equal to rho gamma naught. Okay, and if I had some other constituent of the universe which has a different value of this equation of state w, parameter w, I would get a different relation between the density and the scale factor. That is the first thing that we have to appreciate. Okay. Let me right at this point introduce another component in our discussion. This component goes by the name of the cosmological constant, or lambda. Now, this lambda is also called the lambda is actually, I mean, you may think of it as being a cosmological constant. This is a quantity that was originally introduced by Einstein to general relativity, and the way Einstein introduced it, it is a geometrical thing that appears in the Einstein's equation. Well, as far as we are concerned, we shall think of it as a kind of matter for which the pressure is equal to minus the energy density. So, for our discussion we shall think of it as a kind of material whose pressure is equal to minus the energy density, and the Einstein's cosmological constant has exactly the same behavior. Okay. So, for such a material, for such a substance, the value of W is -1, and you can see that for this rho lambda a to the power 0. So, rho lambda is equal to rho lambda naught. The density is not affected by the expansion of the universe. Okay, it is a cosmological constant, right. It is just that we are thinking of it as a material which fills the universe with a certain density and the pressure which is negative exactly minus the density. It has a negative pressure. Normal substances have positive pressure. Okay. Negative pressure means what is the, let us just interpret what is the significance of negative pressure and positive pressure. If something has positive pressure, if I make this volume, if the volume expands, then the substance which is there inside does work, P dV. So, if the universe, if this volume expands due to the expansion of the universe, the material inside does work, and because the material inside does work, it has to lose internal energy. So, the internal energy density goes down due to two reasons. One is due to the expansion of the universe, other is due to the one is because the volume is larger, and other is it does work. We are looking at the internal energy density. Okay, the density, the total internal energy goes down because of the work done. The density goes down also because the volume has increased. If it were just due to the increase in volume, then the density would fall as a cube. Density into a cube would be constant, but it also loses some internal energy because it does work. So, it rho into a, it falls as a to the power -4 with the expansion of the universe. Whereas, if something has negative pressure, then if it expands, you are actually doing work on that material, you are putting in work into that material. So, because you are putting in work, the internal energy goes up, and if the pressure is exactly equal to minus the density, then the internal energy goes up in such a way so that the density inside remains fixed. The density is getting diluted because of the increase in volume, but you are also doing work which just exactly compensates for that, and the density finally remains a constant. Okay. Now, something with negative pressure is not altogether unfamiliar. Think of an elastic solid. If this were an elastic solid, for an elastic solid, if I have to increase its volume, I have to do work. If I have to increase the volume from the equilibrium position, I have to do work. It is like a spring, right, solid, elastic solid. I have to do work and that work gets stored up as the internal energy of that, as the potential energy of that spring. So, a solid is an example of something that you can think of as having negative pressure. Okay. Here we have the cosmological constant as a material which has negative pressure. Its density remains invariant if I expand the universe, as if under adiabatic expansion. Okay. So, this is the first change that we have to consider if you wish to look at the CMBR or anything else that has pressure. Let us go back to the CMBR quickly. So, the CMBR, for the CMBR, as the universe expands, the energy density for the CMBR, let me just remind you once more, the energy density is equal to AB t to the power 4, and under expansion we also know this is the Stefan Boltzmann constant, should not be mistaken for the scale factor. Further, under expansion we know that A into U, the internal energy density, A to the power 4, is a constant, present value of the energy density. From this we can say that the CMBR temperature so this also is T to the power 4 and there is A to the power 4. So we can say that the temperature of the CMBR into the scale factor is a constant. And the present value is 2.73 Kelvin. So when the universe was half the size, the scale factor was half, the temperature was double, okay, and when the scale factor was 10 times smaller, the temperature was also 10 times larger. So the temperature of the CMBR was the same cosmic microwave background radiation, which has a temperature 2.73 Kelvin, was hotter in the past and at the Big Bang it has an infinite temperature if you just extrapolate it. Okay, so it is hotter in the past. So the cosmic microwave background radiation essentially establishes a model called the hot Big Bang model. Okay, it is the hot Big Bang model, and the fact that it was the past was hot is extremely important in our understanding of the universe. So not only does the energy density in the cosmic microwave background radiation increase in the past, it continues to be a blackbody spectrum that we shall see later, whose temperature is inversely proportional to the scale factor. Now let us go back to our general discussion. In general, we have seen for any arbitrary pressure, a medium with arbitrary pressure, this is how the density will evolve as the universe expands. Okay. Now let us again go back and work out the expansion of the universe. What will happen to the expansion of the universe in such a situation? We have looked at the expansion of the universe assuming dust, where rho into A cube is a constant. What will happen to the expansion of the universe when we consider constituents which have pressure? So one change we have already seen, the relation between rho and the scale factor is modified. There is another change that has also to be incorporated. That change unfortunately cannot be understood in terms of Newtonian gravity, cannot be explained, cannot be handled in terms of Newtonian gravity. The other change that one has to account for is the fact that in the correct theory of gravity, in general relativity, it is not only the mass density which gives rise to gravity. The energy, the entire energy momentum tensor, stress tensor, actually contributes to gravity. So not only does the density inside contribute to gravity, also the pressure inside contributes to gravity. Okay, so that has to be incorporated by hand into this theory. It is not there in the Newtonian theory. Okay, so we shall incorporate it by hand. The change that has to be made is extremely simple. The only change that has to be made is that we have to now not only take into account the mass density inside, but the contribution from pressure also. So the pressure of the material inside this sphere also contributes to the gravitational attraction. That is the only difference. Okay, if you do the full relativistic theory, and that modifies this equation. The modification that we have to introduce is that the density now gets replaced rho now gets replaced by rho plus 3p by c squared. That is the only change that one has to do. So you have to replace the density, the mass density. So it is exactly the same thing, only the matter is substance inside will contribute to the gravitational acceleration. The only difference is that it is not only the mass density inside, but also the pressure that will contribute to the gravitational slowing down. and you have to replace the density with density plus 3p by c squared. Okay, that is the only difference. So, we now have the two equations that we have to solve. Let me write it here. So, the first equation is A double dot is equal to minus 4/3 pi g, and we have to replace 4/3 pi g, we have to replace rho by rho plus 3p by c square, and p we have seen can be written as W times the energy density, or it can also be written as W times rho c square. So, basically what will happen is that this will be replaced by 3 times W into rho. So, so compare it with the earlier equation. We had minus 4 pi g rho a, we now have 4/3 pi g rho a into 1 plus 3w. 3w is basically 3p by c square. Okay, that is the only modification that has to be made. Now, we shall also, you see, in the entire universe, in the universe that we are dealing with, not only do we have galaxies over here, we also have the cosmic microwave background radiation, possibly cosmological constant, and maybe many other things that we are not aware of, like the dark matter, etc. So, we have to account for a variety of components in the universe. So, let us allow for different components in the universe. So, what we shall do is we shall put a sum here, sum over all the components. Each component will have a different value of W, and they will have their own density. So, the equation now becomes this. So, the gravity is due to the superposition of all these different components of the universe. And we have also seen that for each component, rho into a to the power 3 plus into 1 plus w is a constant. So, we can now replace that over here, and we can write it as a double dot is equal to minus 4 by 3 pi g into the scale factor sum over I refers to the different components of the universe, 1 plus 3 Wi a to the power rho I naught. So, I am writing the density of any component as rho I naught. So, for the ith component, I am writing as the present density of that component divided by a to the power 3 1 plus w. So, I will have a factor a minus 3 1 plus into this basically. The procedure to solve this equation, so this equation is an equation involving only the scale factor. The only thing is that here we have a sum of different powers of the scale factor. Now, the way to solve this equation is that we again do the same thing, we multiply this equation by a dot on both sides. So, I will multiply this with a dot. Let me put the a dot here. Okay, so I have multiplied both the right and the left hand side of this equation with A dot. So having done that, now we can see that the left hand side of this equation again is half d by dt A dot squared is equal to, that is the left hand side of this equation. The right hand side of the equation now becomes 4/3 pi g sum over I rho I naught d by dt a to the power minus so the right hand side of this equation can be written like this. We can easily check that if you differentiate this, you will get the factor of minus 1 plus 3 wi over here, and you will get A dot, and what will remain will be minus, I will have 2 here plus 3 wi, which is what we have here also, because here we have minus 3 plus wi and there is a here outside. Okay, so it is quite clear that this is the same as this. Okay, now I can integrate this equation in exactly the same way as we had done earlier, and we then have four-third pi g, we have a sum over I rho I naught a to the power minus 1 plus 3 wi plus a constant of integration, which again I will call E. It is exactly the same thing, only that you have a sum of different powers of A over here. Okay, it is exactly the same except that we have now we will do two things here. We will divide this equation throughout by A square. So if I divide this equation throughout by A square, I will get this. This will become minus 3, and I will have by A square, and let me also multiply throughout by 2. So I will have 8 here, and I will have 2. I will have 8 in the denominator. I will have 8 by 3. 8 by 3 pi g okay. Now we will do two things. First is we will identify this term, we will identify this entire term 2e by A square as a different kind of constituent of the universe. We will not write it as a constant of integration, we will identify this as a different kind of constituent of the universe. We will identify it with something called curvature, and later on when we do talk about the curvature of space and time a little bit, you will see that this term is related to the curvature of space. Okay, so we shall identify this with another kind of component called the curvature. So rho curvature, and I have a 1 by A square here. So rho curvature into A square is equal to rho curvature naught. So, at any instant of time t, rho curvature is rho curvature naught by a squared. This is which is why I have a square here. So, I have basically done that. Okay, so this is equal to 2e. I am just calling 2e rho curvature naught. So, at any epoch this will be rho curvature naught by a squared. Okay, so, at any epoch this will be rho curvature naught by a squared. I am just giving it a name, that is all. I am not saying that it is actually a constituent or anything, I am just calling it this. Okay, so, with this identification I can write this equation as a dot by a squared is equal to, now the other thing is we know that 8 pi g by 3 is h naught square by rho critical naught. The value of the critical density at present is 3 h naught square by 8 pi g. So, this I can replace by where in addition to all the physical constituents of the universe, we also have a fictitious constituent called the curvature, which has gone into this equation. Curvature, so if I identify curvature as a constituent of the universe, let me just see. So, what should be the value of W for curvature? For curvature we want rho into a square should be constant. If rho into a square should be a constant, then 1 plus W should be 2 by 3. If 1 plus W has to be 2 by 3, W has to be minus 1/3. So, this can be thought of as a fictitious component for which W curvature is equal to minus 1/3. If I had a fictitious component for which the pressure is minus 1/3 the energy density, it would behave just like this curvature. Okay. So, in my equation I have accounted for this constant of integration by a square by introducing one extra term in the density which has W equal to minus 1/3, and the entire equation can then be written this way. And I can divide throughout by rho critical naught. So, the ratio of the present density in any component to the critical density is what I call the density parameter of that component. So, this is so with this identification the entire equation takes this simple form that h square t is equal to h naught square sum over all components omega of the different components into a to the power minus 3 1 plus Wi for the individual components. So, this is the equation that you have to solve to determine the expansion of the universe. Further, you also have the condition that at present if you make t equal to t naught, this will become h naught square, this also becomes h naught square, the scale factor has value 1. So, you have in addition to this the condition that sum of all the omega i's is equal to 1. So, this is a very general equation that governs the expansion of the universe in a situation where each component can be represented through such an equation of state. Okay, it is not necessary that each component of the universe can be represented through such an equation of state. If it is so that for each component, my universe has several components, all of which has an equation of state where the pressure is proportional to the density, a combination of such things, then the expansion of the entire expansion of the universe is governed by this single equation like this, where the relative contribution from each component at present is quantified by the corresponding density parameter omega I naught. So, in order to specify a cosmological model fully, you have to specify the value of the Hubble parameter and the value of the different omega I naught, the different density parameters. Okay, once you have specified the Hubble parameter and the value of the different density present value of the different density parameters, then you have specified the entire cosmological model, and this, so this is the, then you can determine the entire evolution history of the universe. So, the main problem then is how to determine the relative contribution of the different constituents of the universe. Okay, and this is the problem of basically determining cosmological parameters. So, in this model there are several cosmological parameters. So, the entire cosmology has been parametrized by certain parameters. One is h naught and the other is the set of the density parameters omega I naught. Okay, if you can determine this, you have determined the dynamics of the universe that we live in, and this has been one of the very important problems in cosmology, to determine the cosmological parameters. Okay. So, our expansion is essentially parametrized in this way. The expansion of the universe is parametrized to these parameters. We may not understand what the microscopic physics of each of these constituent is. For example, I have told you that there is dark matter, we do not know what it is, but we will parameterize its contribution through a corresponding omega for the dark matter. Okay. And you are free to postulate, if observations require it, a variety of other such components. We may not understand what it is, but we will parameterize its contribution to the expansion through a corresponding omega. Okay, so the problem has been simplified in the sense that we parameterize the expansion history of the universe through such parameters, and one is now trying to determine, and one now has a reasonable idea of what are the values of these parameters for our present universe. That is something that we shall discuss later on in this course. Okay, so once you have determined this, then you can use this equation that we just wrote down to solve for the scale factor as a function of time. Okay. In the simplest cosmological model, let me just mention the simplest cosmological model that we have. You will require 4 components. Let me just mention this. In the simplest cosmological model, you will require 4 components. One is the matter, this includes the galaxies, the baryonic matter that we see, and dark matter if it does not have pressure, cold dark matter. So, dark matter without pressure is called cold dark matter. Okay. So, it involves the contribution from all of this. So, this is matter with no pressure, W equal to 0. And then you have a variety of relativistic species, which includes the cosmic microwave background radiation, for which the pressure is 1/3 the energy density, and you have the possibility of a cosmological constant lambda naught, for which W is -1, and you also could have a curvature for which W is equal to -2, -1/3, not -2, -1/3. And I should point out that these two may not be the second one is definitely not matter, it is just parameterizing that constant of integration which is related to the spatial curvature of the universe. So, it is not matter, but we have parameterized it like this. The cosmological constant is possibly not matter, or it may be some kind of matter. Its exact nature is not known, or so this is often called something called dark energy also. This is often given the name dark energy also. So, there is evidence that our universe also has something which has negative pressure. We do not know what it is. The cosmological constant is one such possibility. It is not matter, but there are other candidates also which can produce negative pressure, and there is observational evidence that our universe does have a component with negative pressure. Okay, we shall discuss what the observational evidence is later on. So, you require at least, your model, these are 4 very simple things which you can put into your model, and there may be a variety of other things also which you may, if required, introduce, but we shall talk about the cosmological models in terms of these parameters in our discussion. Okay, and you can estimate this straight away if you know the Hubble parameter for the at least the contribution from the CMBR. You can estimate. I have asked you to do this. So, you know the energy density of the CMBR at present, convert that into mass density divided by the present value of the critical density, you will get the contribution from the CMBR. Okay, so, this is a homework you should do. Please determine the value of the density parameter for the cosmic microwave background radiation. What is the value? The model that we have discussed till now did not have these two, did not have radiation, neither did it have cosmological constant. It had only matter, and it had this constant of integration. E equal to 0, the constant of integration is 0, omega curvature is 0, omega matter was 1. That is the model we have solved, t to the power 2/3. Okay, that is the model that we have solved, where omega curvature is 0, omega matter is 1. The sum of all these should be 1. Okay. Let me also finally introduce something called the deacceleration parameter. The Hubble parameter we have seen tells us the rate of expansion of the universe. It is positive if the universe is, so that is A dot by A. It is positive if the universe is expanding, it will be negative if the universe were contracting, it would be 0 if the universe was static. It has information about the first derivative of the scale factor, which is the velocity. Now, the dynamics of the universe is there in the acceleration. And if we know gravity is attractive, so if the universe is filled, for example, with ordinary usual kind of matter, we expect the expansion to slow down. So, the double derivative, second derivative of A would be negative, and I have in the definition of the deacceleration parameter we have a minus sign. So, this would be something positive if the universe were slowing down. This is what we expect, gravity. So, if you consider an observer over here, a galaxy over here, the galaxy is moving away, but we expect its motion to slow down because of the gravitational attraction of the matter inside. It is this which is quantified by the deacceleration parameter. It is positive and it indicates the slowing down. It is dimensionless because it has 1 by t square in the numerator, 1 by t square in the denominator. Now, let us calculate what this is for the cosmological models that we have been discussing. So, the cosmological models that we have been discussing, the equations can, so this is the first equation that we had, and this equation can be written in the following way. It can be written as, So, this is the equation that we have, forget about the A dot. We can write it in the following way, we can write it as A double dot is equal to minus H naught square by 2. So, H naught square by 2 is 4/3 pi g into the critical density. So, this into a sum over I 1 plus 3 Wi, then we have the density of the ith component, which we write in terms of the present density. So, that will be omega I naught, because this will give you the critical density, which if I multiply I will get the density corresponding to that component at present, into A to the power minus, I have a factor of A over here and I have minus 3 plus Wi 3, so minus 3 into 1 plus Wi. So, I will have minus 2 plus 3 and this is the equation for the acceleration of the universe. We also have the equation for the Hubble parameter. This equation we have just worked out, H naught square sum over I into So, let us use this equation, these two equations, to calculate the present value of the deceleration parameter. So, the deceleration parameter we have seen is the ratio of A double dot by A to h square with a negative sign, and let us use this to calculate the present value of the deceleration parameter. So, we will use this to calculate Q naught. So, at present the scale factor is 1, so I do not have to bother about this. I have minus here and I also have a minus here, so that is gone. H naught square will cancel out with this H naught square, I will be left with half. And sum of omega i's at present is 1. So, this is gone from the picture. So, what I have left is that this is equal to half sum over I 1 plus 3 Wi. That is the present value of the deceleration parameter. So, the value of the Hubble parameter at present is basically H naught square, which cancels out with the H naught square in the numerator. Okay. So, if I have a model which has only matter, nothing else, let us just consider different possibilities. If I had a model which has only matter, if omega matter naught equal to 1, omega matter naught is equal to 1, which means that the other components are all 0, they do not contribute to the density, then what we have is Q naught is equal to half. For matter W is 0, so this is equal to half. On the contrary, let us now consider a cosmological model where in addition to matter we also have some dark energy or cosmological constant. So, we have two things. For such a model we see that Q naught turns out to be half. For matter W is 0, so ordinary matter, so I have half omega matter naught. For the cosmological constant which has negative pressure and the W value of W is -1, this overall factor is -2, which cancels out with the half. So, I have so we see that there is something very strange that happens if you have a cosmological constant in the universe. The cosmological constant causes the deacceleration, can cause, basically the effect of the cosmological constant is that it will cause the deacceleration parameter to have a negative value. If this exceeds this, it will have a negative value. Okay. The deacceleration parameter having a negative value implies that instead of the motion deaccelerating, instead of slowing down, it is actually speeding away. So, the gravity, the sign of gravity gets reversed. Okay. So, if you allow for the possibility of a cosmological constant, then the nature of the gravitational force due to the cosmological constant is exactly opposite that of the usual matter. It causes an acceleration. Okay. So, anything which has an equation of state where W is more negative than 1/3 will cause acceleration, will act with an opposite sign in the deacceleration parameter. Okay. If W is equal to -1/3, it does not contribute to the deacceleration or acceleration, which is quite consistent with what we have been doing, because we have introduced a fictitious component with W equal to -1/3, which is the constant of integration. We do not want it to affect the acceleration, it is just a constant of integration. So, it is quite consistent that if you have W equal to -1/3, it does not affect the acceleration at all. Okay. So, let me summarize what we have done today. In today's class, we considered the possibility that the constituent of the universe can have many constituents, and these constituents can also have pressure. And we assume that the pressure is related to the density through an equation of state. So, first thing that we saw is that if you have adiabatic expansion, then we worked out the relation between the density and the scale factor as the universe expands. This follows from the first law of thermodynamics, the total energy has to be conserved, energy in a volume has to be conserved. Then we incorporated this material, this constituent which has pressure, into the expansion of the universe, and the Newton's laws get modified if there is substantial pressure in the constituent in the gravitating substance. Okay. The pressure has to be comparable to the energy density, only then the pressure is important, and this possibility, we have to allow for this possibility in cosmology. So, we have to use the correct equations which are obtained by just replacing density by density plus 3p by c square, and we worked out what the equation governing the scale factor is, allowing for the gravitational attraction of the pressure also. We worked out the most general such equation. So, this was the starting equation that we had the equation for the second derivative of the scale factor, and we integrated this equation to obtain this. That is basically what we did. Okay. This equation has the entire, tells us everything about the expansion of the universe in a situation where the equation of state pressure is proportional to density holds. Let me finish today's discussion here. In the next lecture we shall look at a few consequences of this equation for different kinds of constituents of our universe.